Welcome. Welcome to this second talk of the SEAM seminars series titled Trustworthiness, Reliability and Material Science for Aircraft Structures. SEAM stands for Surface Engineering for Advanced Materials. My name is Chris Burnt, and as the Director of SEAM, I thank the Australian Research Council, Swinburne University, RMIT University and the University of South Australia, as well as many industries and international participants for their strong support. It is my honour to acknowledge that Swinburne lies on the lands of the Wurundjeri people. Thank you. It is my privilege to dedicate this series to the many healthcare professionals and essential service personnel who have made exceptional sacrifices over 2020 and onwards. To everyone who is listening in, welcome again. Please place your microphone on mute and use the Q&A function to ask questions that will be moderated. This talk on sticking up for glue will be moderated by Dr. Andrew Ang, and my last duty is to ask our host, Professor Rhys Jones, to introduce his friend and colleague, Professor Tony Kinloch. Rhys, over to you.
Thank you very much. It's my honor and privilege to introduce to you all Professor Tony Kinloch, who is a professor of adhesion at Imperial College and a fellow of the Royal Society of London. Tony is internationally acknowledged as being one of the leaders in the field, not just of adhesion, but also of composites, and has numerous awards for his work on durability, fatigue, fracture, etc., not just from the European Union, but also from around the world. With that, I'm going to hand directly over to you, Tony.
Thank you very much, Rhys, and thank you for that very warm welcome. And a welcome to all the audience, wherever you are and whatever your local time is, day or night. And thank you for the organisers for the invitation to give this seminar. It's on my favourite subject, which is glue. And as you can see from the title of my talk, Sticking Up for Glue, I am a real glue enthusiast, also being a professor of adhesion. However, I have to accept that there have been adverse comments about glue from a very early time. Cicero in about 50 BC said all things glued together are weak and easily pulled asunder. And I must admit that some people still share this very wrong impression of adhesives. And even Shakespeare advocated a belt and braces approach to gluing. He said in Macbeth, Lady Macbeth to Lord Macbeth, on discussing the murder of Duncan, "We fail, but screw your courage to the sticking place and we will not fail." And certainly many engineers still believe that a belt and braces approach to the use of adhesives is the best way forward. For example, by putting screws along a glue joint, just to make sure that the joint will never fail. By the way, the use of such mechanical fasteners in the glue joint actually does more harm than good. However, there are some real lovers of glues besides myself, and especially in Australia, it seems.
Beaut, ain't it? The Coral Sea of Oz. This is Hungry Jack's Reef. Around here, the sharks eat the boats. Just a spot to test the incredible sticking power of Solvite All-Purpose. What do you say we whip up a bit of enthusiasm, eh? Here, have some bait, mate. No worries, they're only tiddlers. Quick and smooth mixing. Solvite's just the trick for hanging all papers. And its sticking power? Pretty good, I'd say. Just goes to show. Even down under, Solvite's the only one you need.
However, engineers have accepted the many advantages of adhesive bonding for well over a century. And engineering adhesives were first used in the aircraft industry. Adhesives are based upon polymers, and at the start of the 20th century, we saw natural adhesives, natural polymers therefore, begin to be used by engineers for structural bonding. The earliest World War I aircraft used wood and canvas as bonded structures, and this gave lightweight and stiff and strong structures. And this will be a continuing theme of the talk, really, that when we use adhesives, we often use them to make lightweight but stiff and strong structures, and therefore they're increasingly used in both aerospace and other transport industries such as vehicles, lorries, trains, etc. Now, on from the First World War, in the Second World War, we have the very famous de Havilland Mosquito. It's all wood, of course, as I'm sure you know, and it's actually all glued together. It was developed really so that the furniture industry in North London and elsewhere in the UK could directly contribute to the war effort. Now, quite logically, they used their regular furniture adhesive, which was based upon a natural polymer called casein and was a byproduct of cheese production. The glue was actually sufficiently strong and tough at first for the de Havilland Mosquito, but degraded when it was exposed to hot, wet climates and then completely lost its strength. So when the Mosquito aircraft were sent to the Far East in the very hot and wet climates there, they quickly started to fall apart. But we engineers are very innovative, and the maintenance engineers would put their heads into the wings of the Mosquito and smell. And if they smelt something like very old camembert cheese, they knew to take the plane out of service. So a very early form of a non-destructive test. Later in World War II, the casein adhesive was replaced by synthetic polymeric adhesive, which was a uroformaldehyde adhesive, which was far more durable and did not suffer such problems. In the 1940s, the first adhesive was developed for structural bonding of metals. This was a phenolic formaldehyde polymer toughened by polyvinyl formal. The first jetliner, the de Havilland Comet 1, flying in the early 1950s, needed to keep the weight down. And so this adhesive was extensively used to bond the thin aluminium alloy panels. However, fatigue cracking of the aluminium alloy from the corner of the navigator square window, seems odd these days, doesn't it, having a navigator with a sextant, but that's the way they crossed the Atlantic, led to the complete failure of several aircraft, and all the Comet 1 aircraft were grounded and redesigned over the next few years, but still are using adhesive bonding. Indeed, due to the very extensive use of adhesives, the glue joints were looked at in great detail by the crash investigation team, but were fully exonerated. And today's adhesives are used extensively in aerospace and automotive industries. For example, a common use of adhesive is shown here. Here we have a thin aluminium alloy panel, just a few millimeters thick. And of course, that's all that separates you from the outside when you're flying. But to stiffen and strengthen and reinforce the panel, you can see here Z-shaped stiffeners or U-shaped stiffeners, and these are glued onto the aluminium alloy panel. So notice again really the use of adhesives for thin and lightweight components and structures. This shows a typical wing structure from an aircraft. It's actually a British Aerospace 146. And here we see the U-shaped stringers which are bonded on. The stringers are bonded on here. You obviously can't see the adhesive, but these are the stringers that are bonded on. These two gentlemen, as you might guess, are doing non-destructive testing. They're using an ultrasonic probe here to actually see if the adhesive is in place, is sufficiently cured, and it's of the right thickness. You might ask why there are two gentlemen. Well, it's typical of aerospace inspection, and probably all makes us better when we fly, since this first gentleman is doing the test as the inspector, and this gentleman is inspecting the inspector, just to make sure he does it correctly. Another use of adhesives is in making sandwich components. Here we have a thin skin, two thin skins, top and bottom. Here we have a honeycomb, and they're glued together to make this stiff, strong honeycomb panel. And it's also the way we make wind turbine blades, helicopter blades, and many, many other structures. And of course, without glue, how could you do it? You can't really envisage nailing or screwing this top panel onto the honeycomb panel, so we have to use adhesives. This all comes together in an older type of aircraft using aluminium alloy, like the British Aerospace 146, So we have the fuselage, which is aluminium alloy with bonded on stiffeners and stringers, which are give it its stiffness. We have the honeycomb structure in the rudder and the various control surfaces. So it's using adhesives quite extensively. And in fact, 90% of all the flying surfaces are glued. So when you look out of the window and see that wing flapping up and down, etc., think of all that glue. And if you really are worried, my only suggestion really is to have that extra gin and tonic when at 30,000 feet. And that actually gives you a little bit more trust in adhesives. Of course, we can move on to more modern designs. And this is the new Airbus A350, which, as I'm sure you're aware, is mainly carbon fiber reinforced plastic. So we have a tail section here, which has been carbon fiber reinforced plastic now for at least probably 25 years, if not slightly longer. But of course, the innovation is to have the fuselage made from CFRP, carbon fiber reinforced plastic, as well as the main wings. So we've got carbon fiber reinforced plastic in many parts of the plane, and there's equal use of adhesives as with older metallic aircraft. In fact, you can see this here. This is the part of the equivalent Boeing 787 Dreamliner, and the Dreamliner uses adhesives as well, bonding carbon fiber plastic. You can see here the carbon fiber plastic being black metal, as the engineers like to refer to it. So here we have the CFRP in the fuselage, and again we have thin skins. So again we reinforce the thin skins by bonding on these longitudinal stringers using adhesives to give the fuselage its stiffness and strength. It's not only in the aircraft itself, but it's also in the engines now. If you look at the what's called the front fan of an aircraft engine, and this is what you see if you board up the steps. So if you walk up the steps and look at the engine, you're looking at the front fan. The latest designs replace the front fan from metal into carbon fiber reinforced plastic. You get a weight saving in the fan blades themselves, but you actually get a lower weight saving because the design has to allow for the fact if a fan blade breaks, it's actually contained within the engine. This, if it's a metallic blade, requires the engine casing to be thick, heavy steel, but if it's carbon fiber plastic, then it can just be a Kevlar type fabric. So you also save a lot of weight with the containment. But to protect the front of the fan blade from erosion, and also to cut up any bird that may enter the engine so it doesn't do any damage later on, the blade actually has a thin bonded titanium leading edge, which is glued onto the blade to actually protect the blade during use. Now, if we think about the science behind the technology of adhesion and adhesives, then there's really three main steps we need to consider. Firstly, we need to establish intimate molecular contact and strong, stable molecular adhesion forces across the interfaces between the adhesive and the substrates being the materials we're joining. Now, to achieve this first step, we need the adhesive in a liquid state, but now we wish to harden the adhesive to form a high molecular weight solid polymer which has strength and toughness and stiffness, and which will carry the loads, sustain impact damage, etc. And obviously, as engineers, we really want to ensure and predict the service life of the adhesive joint. So there's really three separate stages we need to consider: the wetting and adhesion, the polymer chemistry, if you like, the hardening of the adhesive, and also as engineers to ensure and predict that the service life of the adhesive is sufficient for its application. We therefore need to bring together surface chemistry. As you'll see, we often need to surface treat the materials before we join them, polymer chemistry of the adhesive, the physics of the process, and mechanical engineering in order to understand the science and technology of adhesion and adhesives. So we truly need the interdisciplinary skills from many branches of science and engineering. And I find that's what makes the science of technology of glue so interesting, is it's a true interdisciplinary subject. Now, if we look at the first of these in a little bit more detail, then, as I said, we need to obtain intimate molecular contact. We refer to that as wetting between the adhesive and substrate, because you need this molecular contact in order to establish the intrinsic adhesion forces that you're trying to get across the interface to keep the joint together. And examples of such intrinsic adhesion forces are van der Waals bonds, hydrogen bonds, covalent bonds. Interesting, and Michael Faraday gave a Christmas lecture at the Royal Institution in London in 1851. And he guessed some of these factors. Obviously, he was unaware of atoms and molecules, but he said in his lecture that the same sort of forces, which he didn't realize quite what they were, of course, but the same forces that hold all solids together will hold different materials together in an adhesive joint, as long as the materials could come very closely in contact with one another. And he was spot on. Now, in order to achieve the above, some form of surface treatment of the substrates is often necessary, and this emphasizes the importance of surface chemistry. Now, on the subject of surfaces, Pauly once said the following comment, and all those that work on surfaces will know how true this is. Surfaces really are very difficult to work on, very difficult to analyze, and they really are the work of the devil. To give an example of this, some work we did a little while ago was on bonding of thermoplastic composites. Now, thermoplastic composites we looked at were based upon polyether ether ketone as the matrix, PEEK, and it's a high performance matrix and widely used in aerospace. So we've got a thermoplastic PEEK CFRP. Now, if we had an epoxy CFRP, which is a more conventional type of CFRPs, these surfaces just need to be clean and free of release agents. But thermoplastic CFRPs need special surface treatments. This is the original sample that we made. We had 2 strips of thermoplastic, that's PEEK CFRP. We glued the 2 strips together with a purple adhesive, and on the way to the test laboratory, the PhD student dropped his sample. As it fell to the ground, it split open. So obviously the wetting and adhesion were very, very poor. In fact, it split open, and you could put your fingernail under this strip of cured adhesive, the purple strip, and actually just peel the adhesive away from the CFRP. One of the other students said this was a nice way of making strips of cured adhesive for tensile testing. You could use PEEK CFRP instead of PTFE material to make your cured strips of adhesive, but it wasn't too well appreciated by the student in question. But it actually turned out to be an excellent PhD project. Of course, the question is, how can you surface treat this material so that you can stick it? Just to show the essence of the problem, it's not quite clear, this slide, I know, but here we have the surface of the PEEK CFRP. So that's here, and we're sitting on the surface, and the surface has only been abraded, and therefore it's not a very good surface treatment. It's the one we use where we got the joint just to break open on the surface of the laboratory floor. But here's a small droplet of the adhesive. You can see it just sits there. It's sort of like oil on a non-stick frying pan. It's not wetting, it's not spreading. We can define a contact angle as this point here, and it's about 90 degrees. So we get very, very poor wetting indeed. And of course, the question that arises is how can you actually treat this material, surface treat it, to actually give you good wetting and good adhesion and bond it together for aerospace applications. The technique we developed is called corona treatment. It's an air plasma treatment. And what we have here is an aluminium plate. Here's an insulating roller. It's a rubber covered roller. If we put a high voltage between the two, we get a spark discharge. You can see that this is a spark discharge occurring here, and we generate lots of ozone and oxygen radicals. Now, if we pass the PEEK CFRP material, these black strips of carbon fiber reinforced plastic using PEEK as the matrix, the thermoplastic material, we pass them under, then what happens, of course, is the oxygen and ozone radicals in the spark discharge here actually chemically treat the surface. So we chemically treat the surface, and as you might guess, we put polar groups, oxygen groups, onto the surface of this material. And here's the result in terms of the contact angle. So now we've got our plasma treated PEEK thermoplastic CFRP. Here's the same volume of droplet of adhesive. And you can see now the adhesive droplet has spread. Here's the surface of the composite. You can't quite see the interface here, it's about here. But you can see that the liquid droplet has spread smoothly and easily over the surface with a contact angle of just a few degrees. Now we can look at this in more detail as surface chemists using a technique called X-ray photoelectron spectroscopy. In this technique, we fire X-rays at the surface and look at the photoelectrons which are ejected. The photoelectrons which are ejected just come from the first few nanometers of the surface. And what they do is to identify the groups on the surface regions of the material. So here's the untreated, just lightly abraded material. And here's the polar groups. There are some, but there's not very many. And hence it has a low surface energy, as you'll see in a minute. After plasma treatment, here's the polar groups. You can see the concentration has greatly increased due to the plasma treatment and all those oxygen and ozone radicals. And here's also is an extra acid functionality. And therefore this surface treatment increases the amount of oxygen on the surface, and this in turn increases the surface free energy. And here's the proof of the pudding. Here we've made adhesive joints. We've measured the adhesive fracture energy. Now this is the toughness of the joint, and the adhesive fracture energy is the energy per unit area required to generate a crack through the adhesive joint. This is shown as a function of the time we've surface treated it for in the plasma. And as you might expect, the more you treat it, the more you tend to build up these polar groups on the surface. With no surface treatment, it's got no measurable toughness at all. Now the surface energy of the material at this stage is about 40 millijoules per meter squared. And it fails interfacially to the open points. After about 20 minutes, the surface energy is now 70 millijoules per meter squared due to the presence of these polar groups. We've increased the surface energy, and theory, wetting theory, tells us that to get good wetting and hence good intrinsic adhesion, the surface energy of the substrate, gamma S, should be greater than that of the adhesive. Now the adhesive is about 45 to 50. Down here we obviously haven't met this criteria, and therefore we get poor wetting and adhesion, while up here we get the surface energy of the PEEK carbon fiber composite to be 70, greater than 45 to 50 of course, and therefore we get excellent wetting, very good adhesion, and we get cohesive failure through the adhesive layer itself. So the failures in the glue, and that's why it plateaus out, and we have a toughness of about coming up for 4,000 joules per meter squared, which is very, very good indeed. So you can see the surface treatment is terribly effective for these thermoplastic fiber composites and is widely used now by industry. Moving on to the next stage, and this is concerned with hardening of the adhesive. Now, to achieve the earlier requirement of good wetting and spreading, then we needed a liquid adhesive to spread over the substrate, get intimate molecular contact, and achieve these high level of intrinsic adhesion forces. But now, of course, as engineers, we want the joint to withstand high loads, be tough, etc. And therefore we have to harden the adhesive, or cure it as it's termed, to form a polymeric solid. And this really emphasizes the role of polymer chemistry and physics. Now, I like to mention physics here and claim to be a physicist because Ernest Rutherford, Lord Rutherford, was once asked what he thought about other disciplines. You know, what about these chemists and engineers, etc. And when asked this, with disdain in his voice, apparently, he said, so I'm really representing this from the standpoint of we chemists and engineers who are just simply stamp collectors, but I think still quite important stamp collectors. Now, to harden the adhesive, for structural adhesives, engineering adhesives, we tend to use a chemical reaction. And therefore we have an epoxy adhesive, which are very widely used and are cured by the addition of a second component and possibly with heat. I'm sure you're all familiar with two-tube aldite. One tube is the adhesive and one tube is the second component hardener. Other adhesives like super glue, cyanoacrylates, cure by moisture, and that moisture is present on the materials you're trying to join, and metals always have some moisture present at the molecular level, and that's why super glue works great on metals. Plastics don't have that level of moisture, and therefore they are not so good when using super glue. And other adhesives like acrylics cure with UV light, and they are widely used in the electronics industry. But as materials engineers, we can also take the advantage of the hardening process to chemically design the adhesive to possess a multi-phase structure on the micro or nano scale. And this can lead to a very tough, impact-resistant glue. So many engineering adhesives are based upon epoxy adhesives with a toughening micro rubber or nano glass or nanocarbon phase of very small particles present that give this multi-phase material, which can be very tough. And this shows an example. This is a transmission electron micrograph of a rubber toughened epoxy, which is really one of the mainstays of the engineering adhesive range. It's typical of an aerospace adhesive. What we have is the epoxy. Ignore the black lines, they're just chatter marks when we are sectioning the sample, but what we really are seeing is the cured epoxy phase, and then the black spherical particles are the rubber particles. They're about 1 to 2 microns in size, as you can see. There's usually about 10, 12, 15% maybe by volume of such rubber particles. Now, the presence of the rubber particles means that when the material is stressed, at a cracked tip, for example, there will be a stress concentration of about 2 around their equatorial plane. And this stress concentration in this area is good because the stress concentration arises from the difference in modulus and Poisson's ratio between the rubber and the matrix, and the stress concentration causes plastic deformation and energy absorption in the epoxy. So the rubber particles really act as catalysts in a sense for plastic deformation in the epoxy, and this can lead to higher toughness values by up to a factor of 20. So it's really very, very impressive. This shows an example, a non-aerospace example. I thought it was rather nice. This is the Aston Martin Vanquish. Here's a close-up of the chassis. The chassis is made from aluminium alloy, lightweight, fast, quick car. As you might guess, the orange squeezed out material here is the rubber toughened epoxy. And there's really only glue holding this chassis together. There's a few fasteners they use just to put it through the curing oven, but the whole will load and toughness is carried by the bonded joints here. And that's true even of the crash resistant zones they put into the car to protect the passengers in case of a crash. Now, all of this car can be yours for about $500,000 Australian dollars. And if you really want to stick up for glue, I think trying to buy one of these cars is probably the way to show that you're a real glue enthusiast. And this is a practical test of such adhesives. A rather older Formula 1 car, but the idea is still being used. The driver's cockpit safety nacelle here is made from carbon fiber reinforced plastic, lightweight of course, and it's all glued together. So the safety zone is carbon fiber reinforced plastic glued with rubber toughened epoxies. And in a crash like this and others, I've never heard of the adhesive joints ever failing. And in fact, the driver was the German driver Wirtz here at the Canadian Grand Prix, and he got safely out of the car, this was during practice, got into another car and carried on. So they really work extremely well, these rubber toughened glued carbon fiber composites for racing cars. Here's the more recent work we've been looking at. This is another toughened adhesive, but now using in situ nano glass particles. We use a sol gel technology, so that these glass particles, this is a transmission electron micrograph, they're about 20 nanometers in diameter. You get very good dispersion, which you need to get good toughness, but they're formed in situ, so this leads to the good dispersion and also overcomes any health issues. Since these nanoparticles are never free in the atmosphere, they're always contained within the adhesive because they're formed in situ. Also, you get a very low viscosity for the matrix, which means you can use it also for composites, especially for resin transfer molding. You still maintain transparency, you still maintain temperature resistance. So it's another way of toughening the adhesive. This type of adhesive found very quick application on the Airbus A350. The vertical stabilizer here is CFRP, and it was found that they were getting erosion of the CFRP, and therefore what they did was to apply a coating of this nano glass toughened epoxy, and it gave them excellent toughness and erosion resistance on the tailplane of the A380. More recently, in work with RMIT and the University of New South Wales and friends and colleagues there, we've been looking at using graphene nanoplatelets and carbon nanofibers to actually toughen the adhesive. Further, what we've done is actually align the materials inside the adhesive layer. Now this shows work for graphene nanoplatelets at 1%. It's successive time frame, 0 minutes, 4 minutes, 10 minutes, 20 minutes. Here would be one carbon fiber reinforced plastic CFRP substrate. We're gluing together CFRP. Here would be the second CFRP substrate. And we apply AC field between the two substrates. And as we apply the AC field, you can see that we start getting alignment, in this case, the graphene nanoplatelets. So we actually align the graphene nanoplatelets inside the adhesive layer. Obviously, we do this while the adhesive is liquid before it gels and cures. So we do this early on in the process. And here's the aligned GNPs. You can see we get rather nice chains. And bear in mind, of course, there's one CFRP substrate there, another one there, and the crack will try to travel down through the adhesive. And therefore, these chains of GNPs actually help increase the toughness even further. Now, to show this, here's the results. Here's the fracture energy against the toughness of the joint we're looking at. This is the amount of GNPs or carbon nanofibers. You can see that the carbon nanofibers in red are more effective than the GNPs, the graphene nanoplatelets, in black. And this is because we get more pull out and void growth associated with carbon nanofibers. And we've published this work and we can model it theoretically as well. The other interesting thing we see is that for several of the levels of added nano reinforcement, until we get the too much, when it actually makes the material, the adhesive, too thick, too high viscosity, then the alignment of the material by applying the AC field gives you slightly higher toughness for both the CNS and the graphene nanoplatelets than for the random material. We also see, as you might expect, of course, an increase in electrical conductivity in the nanocomposites. Hence, they can be used as damage sensing materials to detect fatigue crack growth and or possibly improve resistance to lightning strike damage. So it gives you really a multi-purpose adhesive that not only is tougher, but has other applications too. Now, if we come to the last aspect I mentioned of increasing and predicting the durability and service life, then this is a news clipping from 2003. If you're speaking about things that go wrong, it's always good to speak about old things that went wrong and have been cured and now time passed. And obviously Concorde has been taken out of service, not for this reason, of course. But in 2003, you can see it lost part of its rudder halfway across the Atlantic. The plane landed safely. A spokesman said that it doesn't affect the safety of the aircraft, which is very true, of course. And the investigation team found that the aluminium alloy skin had completely come away from the honeycomb. Remember that early honeycomb I showed, where you have a honeycomb core, a skin that's glued, and the two had completely come away. And they found this was due to water entering the joint and attacking the adhesive metal oxide interfacial regions. A picture is always worth 1,000 words, and here's a picture. This was an earlier flight. This was actually at Sydney Airport. This was a charter flight from New Zealand to Sydney, April 1989. There used to be a rudder section here, which is no longer there, fell into the sea. Again, water was found to have attacked this whole rudder section, and some of it failed. And of course, the reason the aircraft landed safely is because there's a redundant second rudder here as a safety sort of backup. Always good when you fly to think they've always got these safety backups for you. And it was this rudder section, of course, which allowed the plane to land safely. As I said, the basic problem is really the attack on the interfacial regions between the adhesive and the oxide. And water gets in, attacks these regions, weakens them, and possibly leads to this problem of early service failures. So you can see that the surface pre-treatment for the metallic substrates is likely to be an important factor. In fact, it's the key factor in determining the long-term durability of the joint in hot, wet environments. And we've undertaken basic research in the role of surface treatments in influencing the durability of adhesive joints to water. This shows aluminium alloy. It's a section, so you're looking at a section through of aluminium alloy. And the standard treatment for aerospace for aluminium alloys is to anodize. You put it into acid and pass a current through the aluminium alloy, through the solution, and this generates an oxide layer. This oxide layer is about 500 nanometers thick. This is the top surface to which you would apply the adhesive, for example. Here's the aluminium alloy underneath it. Remember, this is a side section, so you're looking sideways on. And it's rather like a collection of empty drinking straws. You can see there's a hollow here, potentially into what an adhesive could get into to fill. So you're really looking at a side section of open-ended drinking straws, which forms the oxide on top of the aluminium alloy. But it's actually quite a complex technology. And what we found in the research we asked to undertake was that if you applied just the epoxy adhesive straight to the oxide, you actually got poor joint durability. And we wondered why. And the reason is here, this is a section again, so we're looking sideways on. This is an energy filtered TEM. And energy filtered TEMs allow you to identify elements. So we have the adhesive here, which obviously goes off the slide into the distance. Here's about the half a micron, 500 nanometers of the oxide generated by phosphoric acid anodizing. Here's the aluminium alloy. Now the blue is carbon, the green is the oxygen obviously from the aluminium oxide, and this is the aluminium alloy underlying the oxide. But the important thing to see is there is no blue penetrating into the oxide. So there's no adhesive at all penetrating into the oxide structure. The adhesive is simply sitting on top of the oxide. And remember, this is like open drinking straws. And therefore, what you get is a very weak interface, and water comes in, goes into the empty drinking straws, which is the oxide, attacks and weakens the interface and the oxide, and you get premature failure. Now, the way of avoiding this is to apply a primer. So you can apply a primer, which is a very low viscosity material, usually an epoxy, and usually the opportunity is taken to put corrosion inhibitors, coupling agents to aid bonding, such as chromates, phenolics and silanes. It's really like a witch's brew into the primer. Now, the primer layer is usually about 100 microns thick, and therefore on this scale the primary layer is off the slide, and then the adhesive layer is applied on top of the primer. But the important aspect is really the primer oxide interface. So you can see now the primer, and carbon is blue, remember the carbon penetrates deep into the oxide. So you get primer penetration into the oxide. So you actually form a micro composite interface region. No longer does the adhesive or primer just sit on the top, it actually penetrates into the structure. And when you do that, you get excellent long-term durability and excellent resistance to water attack. And I'm sure you'll all be pleased to know that aerospace companies always use anodization treatment followed by a primer before they apply the adhesive. And by this technique, they get excellent durability, and also by applying the primer on top of the freshly treated oxide, they can actually store the primer treated oxide for some time before they have to adhesively bond it. So it's a manufacturing aid as well as an aid for durability. Coming to service life predictions. Now, on predicting the service life, Niels Bohr once made the famous statement, which I'm sure is very, very true, and prediction is always a nightmare. If you're doing modelling, it's always best to know the answer before you start, but obviously in real life that's not the aim of really doing quantitative predictions. Now, I've tried to avoid, as you see, equations in the talk, but I can't really avoid it here. So if you don't like equations, and we're coming near the end of the talk, of course, now's the time to go and make a quick cup of coffee, or if you're on UK time, maybe fill up the glass of wine. This is work doing jointly between myself and Rhys Jones, our chairman. We've been looking at life prediction under cyclic fatigue loading, where of course you cycle the joints between a maximum and minimum load. And to skip quickly through the slide, we base it on a fracture mechanics approach. So we have the energy release rate, and we relate to this stress intensity factor, which is involved in the Paris law. Now, the K, the stress intensity factor, is proportional to the square root of the energy release rate, and therefore we define this term delta root G, and that's defined here, where delta root G is given by the maximum energy release rate in our cycle, which corresponds to the maximum load, of course. And here's the minimum energy release rate, which corresponds to the minimum load. So this is max load, min load, max load, min load, as in a fatigue cycle. We can also define a threshold term. Now, delta root G1 threshold is the value of the energy release rate, this term, below which no cyclic fatigue crack growth is seen. So it gives us a lower limit to the point at which we see cyclic fatigue crack growth. Now, we've expressed this and embodied it into what's known as the Hartman Shrive equation. That's this equation. And this equation relates the rate of crack growth to constants D and N. A is the fatigue equivalent of the fracture energy. So we can relate the rate of crack growth per cycle, dA dN, to our energy release rate range here. Now we can do that by getting all the experimental data from short-term fracture mechanics tests, and we get one master curve, and we get that by varying somewhat the value of delta root G1 threshold. So by relatively small variations in this term, we can fit all our short-term data onto one master Hartman Shrive plot. And that therefore gives us a mean value of this term. And we also get the standard deviation. So now we can use this term coupled with its standard deviation to make long-term predictions using this Hartman Shrive equation. And the Hartman Shrive equation is actually widely used in terms of stress intensity factors by metal engineers, metal aerospace engineers. So they're well versed in this, which is also useful when you start talking to aerospace engineers that are doing the design for various industrial companies. Now, to see how it works out, this is some experiments. It's from a very good friend and colleague, John Allen Pascoe, who's now at Delft University. And this is his experimental data with our theory put on top of it. And essentially, he took an aerospace adhesively bonded repair. He measured the crack length here as a function of the number of cycles. He looked at the crack from two sides. So we got two measurements from side 1 and side 2, which is a nice comparison. He did two different maximum loads in the fatigue cycle. Maybe just look at this one. It's easy to see. So there's a maximum load of 150 megapascals in the fatigue cycle. Here's how the crack is growing as a function of cycles and experiments from side 1 to side 2. And here's our theoretical predictions. This is for the mean value of our threshold. And here's the value -1 standard deviation, and here's +1 standard deviation. So we've got mean and 1 standard deviation either side, which we obtained from the short-term fracture mechanics test. Now we can do long-term predictions. As you can see, the theoretical predictions agree with experiments very well. They capture the data extremely well. There actually are no fudge factors, empirical factors at all in this. It either fits or it doesn't. As you can see, it fits quite well. And this is the sort of work that Reese and I are now working on for adhesives and for composites. And it's looking very good in other structures as well. So it's looking like a very nice approach to actually predicting the cyclic fatigue long-term life from short-term fracture mechanics experiments. Some final thoughts on adhesion and adhesives. This is Drosera rotundiflora, otherwise known as a sundew plant, and it lives by digesting the body juices of dead ants. As you might guess, it has to capture the ant first. It doesn't capture the ant by screwing it or nailing it down. These are droplets of glue. So it's obviously going to glue the ant. And here is the glued ant. Here's the ant. And it's caught. Here's the droplet of glue. And notice that the plant knows all about contact angles. Look at the very low contact angle here, just a few degrees. So we've got very, very good wetting of the glue over the body of the ant, and very good intrinsic adhesion. And it doesn't use rubber toughened epoxies. It uses a natural adhesive. I don't think there's any rubber toughening in it to my knowledge, but look at the plastic deformation. Look at the toughness of this glue droplet. Extremely tough, high plastic deformation. So it knows all about tough adhesives as well. And what's more, the plant doesn't die when it rains. It can capture wet ants just as well as it can capture dry ants. So I think nature's always an inspiration to us engineers, and so the sundew plant is no exception here. Good wetting, good adhesion, tough adhesives, and it does it to wet ants as well as dry ants. And as a last, very final thought, don't forget, and thank you very much for your attention, and stay safe, and thank you everybody for listening. If you hear a little crackle there, by the way, that is a bottle of very good Margaret River Shiraz being opened. I think I deserve it now, and I thought I've got to have some Australian wine, which of course I enjoy since I go to Australia every year when I'm allowed to. So I'm now imbibing a very nice glass of Shiraz, and thank you for listening again. Chris.
Tony, first of all, thanks very much. I have a very basic question. You indicated that the belts and braces approach, the screw and glue, does not work. Intuitively, I don't understand that. Can you please expand on that?
Well, of course, what you do by putting chicken rivets in, often as the industry refers to them, or mechanical fasteners, is compared to the purely glued joint, you're putting holes and stress concentrations in. So you don't really want to put holes and stress concentrations, and also that is another path for water getting in. The Concord rudder that I showed, the real problem there was the original design was fine, and they decided they'd put like little aerodynamic foils on the side of the rudder of Concorde, and they did that with mechanical fasteners. And over the years, water got in through the mechanical fasteners into the glue joint, and that's why it failed. So, you know, apart from the cost of doing it, of course, putting in holes and mechanical fasteners and putting stress concentrations into your joint, and often they put them into the very end where you get high stress concentrations, doesn't really do very much. People used to do it with very brittle adhesives many years ago, going back probably several decades now. The adhesives were brittle, and you did get cracking at the end of the joint, and they'd put what the industry always termed a chicken rivet in at the end of the joint. But really, with the development of these rubber toughened adhesives, which are extremely tough, very fatigue resistant, putting chicken rivets in isn't needed, and it also actually loses you strength, and certainly loses you probably durability.
Okay, so the second question comes from Marcus, and it revolves around generating ozone and free radicals.
I wonder if that's Marcus, my son-in-law, who says he's going to listen in from Sydney.
We don't know.
So Marcus, your potential son-in-law, wants to know whether this can be done at the commercial level, commercial manufacturing level.
It is indeed. It is done. It's done at the commercial level. You can get very large, different. I just showed one type of air plasma, but there's a whole range of air plasmas, and also you can do plasma treatment in a high vacuum, and that's not quite so easy to do for adhesive joints, but it's widely used for bonding films together for packaging, etc. But coming back to engineering adhesives, there are various other air plasmas which are used, but the corona plasma is very easy to use, and actually the aerospace people have developed a almost, I was trying to describe it really, it's something, it's almost like a pad you use. It's maybe 30 millimeters or so, 60 millimeters in diameter, and you can just apply it over the area you're going to repair. So it's often used for repair. Obviously bonding is used for repair, so it is actually quite easily and readily used by industry. And the corona treatment idea really came from the package industry. They've got those corona treatment devices. They are up to, you know, maybe 2-3 meters wide for the packaging people, so it's very common, easy to use. You can also use other treatments, and we use chemical treatments, but obviously industry is going away from chemical acid treatments these days, and therefore much more interest in plasma type treatments.
Okay, so we've got several questions from Chung Wang, but we'll just go through them one by one.
Oh, no, we can't allow Chun to ask me questions. He's my colleague and co-author who did the graphene work with, I showed.
Well, he has a question, and here it comes.
Okay, Chun.
The toughening of the adhesive depends on dispersion of the particles.
Yes.
What is a good quantitative tool to characterize or rank the degree of dispersion?
There are such tools, and we publish work on it. It's not my expertise. I've done it with people whose expertise, so to speak, it is. Usually use TEM or SEM, and then some quantitative scanning technique to get your dispersion, and then you feed it into a mathematical analysis, and you can analyze it statistically. And there are papers on this. We've published one ourselves. Felicity Guild comes to mind, and Ambrose Taylor, a colleague of mine at Imperial, usually working with statisticians. So it's usually via SEM, TEM, quantitative assessment, and then a statistical analysis, and you can get dispersion factors out of this. If you ask the more difficult question, how does this relate, and what should the factor be to get you tough materials? I don't really know. I could just say in a hand waving sense, we know you need a good dispersion. You want to avoid agglomeration if you're going to have your particles really increase the toughness. But it's a very good question. It's still something people are scratching their heads about.
So John Allen Pascoe from Delft, TU Delft,
who I quoted. Thank you, John Allen, for the work, and it was a very nice work. And
so why do you think airworthiness authorities are still so hesitant to certify bonded primary structures? And what can we do about it?
Well, that's straightforward in a sense. It's lack of non-destructive testing. if you go to the latest FAA, Federal Aviation Authority regulations, it says you obviously can use adhesives in secondary structures, and that's why they're used at the moment as load-bearing structures in their own right. If they fail, they will not cause a loss of the aircraft. If you go to primary structures, it actually says you can use adhesives for primary structures now. But you read through 10 pages, at the very end it says the above is only relevant if you have a non-destructive test which will detect lack of adhesion. And that's the test that is the killer. You can detect whether the adhesive is cured and its thickness and whether it's actually there. I've known instances where people have forgotten to put it in, but non-destructive testing will detect that. But if you say to non-destructive testing, my adhesive and my substrate are in contact, but there's no adhesion there, it can't detect it. Think of putting a soft rubber onto a piece of glass, then there's no strength there really, but NDT will say you've got a perfect joint. So you need, what holds it up is a non-destructive test technique for detecting what we call a kissing bond. That's where the substrate and adhesive in contact, there's no real strength, no adhesion forces have been generated. There's no such NDT technique. People are trying still very hard. If any of the listeners have got techniques, ideas, I would say do it in the garage if you can, develop it, patent it, and you'll be a millionaire by the end of the year. Because everybody's desperate for it. Various companies have said, I'm not going to use, apart from FIA, they say we will not use more adhesives until we can detect this kissing bond problem by non-destructive testing.
Thank you, Professor. Andrew here. I just want to jump in. You've got a fan club here. Nisha is a good friend of you. He has a question about your comments on block copolymers. Have you tried it, and does it actually improve the properties of the epoxies that you work with?
It does indeed. We've done work on this, and there's lots of work. I'm trying to remember the gentleman's name; it escapes me. In somewhere in Minnesota, maybe the University of Minnesota, block copolymers have been used. The rubber toughening agents themselves, in a sense, block copolymers. They're typically carboxy turbinated butadiene acrylonitriles. They tend to be block copolymers, and they work very, very well. Really, what you're trying to achieve in these block copolymers, rubbers, etc., is this second phase of rubbery material with a low TG. So they are widely used, and also so are core shell materials as well. Core shell rubbers are another type of rubber that's widely used. The CTBNs of carboxy terminated butadiene acrylonitrile rubbers, which I showed, tend to be the standard ones, not least because if you speak to the aerospace companies, for example, mention a new glue or a new composite, they say at the moment, no thank you, we just want to make some money, some profit. Every time you requalify a material, you're talking about $500,000 to qualify it. So nobody's very keen on qualifying new materials for aerospace unless they really have to. And these rubber toughened adhesives have been performing for the last 30 years extremely well with very little problem. So it's a product they know and love, and at the moment staying with them. But these other core shell materials, block copolymers for specialist applications, they all have their places, just like our nano silica does.
Great. Thank you, Professor Kinloch. And with that, I'm also pleased to announce that Professor Kinloch has agreed to provide a recording of this presentation. It will be on the SEAM website. So while you're visiting the SEAM website, can I also request that you subscribe to us, and so they can stay in touch? And please also allow me to introduce to you top 3 of this series on aircraft structures. Top 3 will be given by Mr. Lawrence Molland, AM, and it will be on how to design a fail-proof aircraft like a black box recorder. So for those that know Mr. Lawrence Molland, AM, he was the former DST Group Head of Emerging Aircraft Structures and Structural Integrity. He's currently now a consultant and trainer in aircraft structural integrity, air accident investigation, and novel fatigue analysis method. Okay, once again, I would like to extend my heartfelt gratitude to Professor Tony Kinloch for his time this evening. And I really look forward for you to visit Australia again soon. Hopefully we can have a bottle of wine, good Australian wine. And cheers and goodbye for those who have joined us today. Thank you very much again, and see you.
Thank you very much, Andrew.